Being that most of you in the room have had a course in physics before, this shouldn't be a particularly hard thing to talk about for the next few minutes. Near the surface of the Earth, if I place an object some distance above the ground, you should be able to tell me the force of gravity that acts on this object. Can you? Really, nobody remembers how to do the force of gravity on an object? Many of you passed first semester physics. Some of you passed the AP1 and mechanics exam. So, thank you. The force of gravity, also known as weight, is just mg. It wasn't that hard. So that's good. At least we can think back to that one. It didn't really matter how big the object was. We knew that to find its weight, we needed its mass times the acceleration of gravity. You guys remember that? We also made this interesting observation, although I'm not sure you made this as an observation, but the acceleration of gravity was relatively uniform everywhere near the surface of the Earth. And so we would use 10 meters per second squared as a means of as our acceleration, 9.8 if you thought you were being so technical. But the idea was that near the surface of a large object like a planet or a moon, the acceleration of gravity was relatively consistent. Now, what we were actually doing was finding the size of the gravitational field. It's not what the result was, because the result ended up being an acceleration. So we treated problems in Earth's gravitational field as free fall problems, and as free fall problems went, we just assumed that there was this uniform acceleration. Later in the year, whether you were in AP1 or mechanics, we talked about what it would take to find the acceleration of gravity due to a planet or due to a moon. And we would do things like, if you are some distance away from a planet, you could find the force of gravity between you and the planet. So we'd say this is the mass of the planet, this is the mass of you. And then we use the Newton's law of universal gravitation. To calculate the force of gravity between the two things. And then I said, well, let's practice this on the Earth and put you right near the surface of the Earth to figure out what your force of gravity would be. We use the radius of the Earth here. And if you remember this, what I had you do was take the mass of the Earth, the mass of u and g, and divide by the radius of the Earth. Now, I don't know the mass of you guys, but I do know the mass of the Earth, which is about 5.96 times 10 to the 24th kilograms. I know you're not writing it down, but in a few minutes you're going to ask me to repeat it anyways. .96 times 10 to the 24th kilograms. And the radius of the Earth, which I'm blanking on at this moment. So mass of the Earth, radius of the Earth. 6.38 times 10 to the 6 meters. 5.96 times 10 to the 24th kilograms. And I'm afraid you probably don't remember G from last year. I'll give it to you. Now, I don't know the mass of you, but I'd like you to estimate. And that way you could find the force of gravity this way as opposed to just doing mg. Now, I have a reason for doing this, so if you would finish this off, that'd be great. If you don't know what your mass is in kilograms, take your weight in pounds and divide by 2.2. You'll need a calculator. I don't think most of you are going to be able to do this in your head. Now, again, what this does is it gives us the force of gravity on you from the planet, which is also the force of the planet, the force of you on the planet. This is the force of attraction due to gravity. Now, if you're done, and I hope that you are, you may remember what we did last year with this. You see, last year, in order for everybody to kind of see something, I said to take that force of gravity that you have, divide by the mass of you. Now, if you did that, we'll know if you are doing things correctly, because right now you should be looking at the acceleration of gravity. You should be looking at 9.8 meters per second squared. If you're not, you don't push buttons very well, and your button pushing needs to be repaired. But I'm very confident that you should be looking at 9.8 meters per second squared, because what we have done is set this equal to ma and divide both sides by m, leaving us with what the acceleration of gravity should be if you were to be dropped near the surface of the Earth. Now, the best part about doing this with all of us here today is to recognize that we started kinematics with the assumption that there was a uniform acceleration near the surface of the Earth, and allowed students who are young, who are trying to figure out physics for the first time and are just dealing with the quantities of motion, to have an experience of free fall problems. And part of the reason is because we can do a whole bunch of labs with them that are pretty straightforward, dropping stuff and rolling stuff up ramps, things like that. And it gives us a good touchstone for understanding the vocabulary associated with motion. But what we've actually done is we've taken a force and divide by a force carrier. Force carrying value. I bring it up because what it did is it told us something about the space where this object was located. I mean, this part's hard to understand, but when we did free fall problems, the whole first semester, when we talked about dropping something off of a building or throwing something into the air, you never had to ask whether you were dropping something small or something big. We just assumed that these objects would all fall with the same acceleration, even though they're all experiencing different sized forces. The force on the larger object is larger, mg, because the mass is bigger. But the acceleration was the same for all of them. In fact, one of the things we became pretty aware of is that if all objects fall at the same acceleration, I don't really care about the object at all. I care about things like how far from the ground the object was, and perhaps did the object have some starting velocity. We made this about motion problems and not about what was really causing the object to be pulled downwards. We have found other times where knowing something about the space has been more valuable than knowing about the specific objects located at that space. In order to fully appreciate this, I want to ask you, what pulled the rock or the pebble downwards? We say a word like gravity, right? And generally is the easy answer, because it's a word that you associate with things that get pulled downwards. You've probably been told by me that that's what did it, but we don't know what that is. Right? There's nothing that connected the rock with the earth. Nothing tangible, nothing physical. There's no connection point. There's no strings or some kind of structure that connects the two things together. I merely drop objects or push objects off my desk, and a magical hand reaches out, picks them up, and pulls them down. We don't have all of the answers. We have a set of mathematical relationships that predict behavior based on what we observe, but the mechanism, the thing that causes this to happen, isn't fully understood. There are theories. And as I said last year, I think I spelled field wrong, so I'll correct myself. I am a field effect theorist. Just a high school teacher. It makes me sound smart to say things like this. I believe that there's something that fills the space. That an object like a planet that is planted in the middle of space, because it is big, changes the nature of the space that is there. Causes a dent, if you will, and objects fall into that dent. I believe it profoundly, that if the planet weren't there, and I didn't show up, I am relatively small, but I cause a small dent. But if there's nothing else out there, nothing happens. But if I bring the planet in, or something similar to a planet, something big, it changes the nature of the space, and because it does, it caused me to move towards that object. Of course, I have also changed the space, and there's a force on that object. Now, the forces act independently. The force on this object is going to be much different than the force on this side. In fact, I'd argue that I am very unlikely to move the Earth, but the Earth is very likely to move me. Does that make sense so far? And this is a review of the things I would have talked about when it came to first Newton's third law, and in this context, the force of gravity between two objects. I believe the connection between those objects is something that is done to the space, that has made the space different, and therefore that connection causes a force. Now, there are other theories. This is just one. Particle exchange theorists believe that there's an exchange of particles here, and that there is a force-carrying particle that sends information about the size and direction of a force that should be experienced between two objects. I don't know that I buy into that, but there are people who are searching for the graviton particle in order to show that it is a connection due to the existence of these particles. I don't know what's actually happening. And I'm not going to spend a lot of time theorizing because, quite frankly, if I can't get you to do your regular homework, we don't get to talk about the interesting stuff that might be out there. We know, ultimately, that there is the possibility of a force to exist between objects with charge. And this is a little different in that this force causes both repulsion and attraction. So I posit that there is an electric field in the same way that there is a gravitational field. But this field is going to be a little different than the gravitational field because the gravitational field was always an attractive force and therefore always directed in a similar fashion. The difference is that when we went to calculate the size of the gravitational field, we were doing so in a manner that kind of hid the fact that we were looking at a field because, unfortunately for us, the same thing that causes gravity is the same thing that causes inertia. So when we took the force of gravity and divided by the mass of an object, we got something that was an acceleration. But this is because we took something that caused gravity and divided by the inertial mass. And in so doing, we got this weird case of G being an acceleration. We were calculating the size of the gravitational field when we were doing that. The gravitational field and all fields are supposed to represent something about the space around an object, and not necessarily something about the object experiencing that force. That's what a field is supposed to do. It's supposed to tell us about the space and not what happens to specific objects. So we are going to define the electric field as the force experienced by a test charge, sorry to bore you, divided by the value of the test charge. Again, we are going to define electric field as the force experienced by a test charge divided by the value of the test charge. Okay, you guys got that in your notes? So to understand this, one charge becomes the main charge, and one charge becomes the test charge. The idea is that the test charge is small enough where its contribution to the electric field in that region of space is small. I'm going to say that again, because I want you to understand this, but I also want you to make it clear that the test charge is intentionally meant to be small, because we want its influence over the space to be minimized, so that the overwhelming electric field is that of the main object we're observing. Now, up until this point, we've only been using one formula to deal with finding a force between two charged particles. We've been using Coulomb's law. I also need to tell you that this is not the only way to find an electric field. It's just your current way. But since it is the only way that you know, we've been trying to find ways to use it in even more unusual circumstances. In circumstances where we didn't have point charges and we had some kind of charge distribution. So we have found ways to sum the contribution to a large-scale force by taking an object and breaking it up into lots of little pieces and taking two pairs at a time. And over and over again, adding up all the contributions to that force to come up with one force between the two objects. That's what we have spent the last week and a half doing. Now, I am defining electric field, and I'm defining it in terms of the force experienced by that charge, which is going to be in newtons, and the size of one of those charges in coulombs. Which means the electric field has these weird units of newtons per coulomb. And because force is a part of this, the electric field is a vector quantity. So electric fields are things that fill space around charges, and they cause the force to act on other charges in that space. Do I need to say that again, or is that one time good enough? Right? Faster. All right? Electric fields fill space. They fill the space around charges. These fields cause forces on charged particles in that space. Let me give you a for instance. this should be familiar. Keep it like I have it. Do you remember us finding the force on charge Q due to 2-point charges? We were located on an axis that passed through the center between those two charges, and you were asked to find the force on charge Q from these charges. You guys remember this? It's in your notes. So at any moment right now, I should say, look it up and come up with the expression. What I mean is I would like to know, what did you write here? And if it's not in your notes, well, you might have to do the work to figure it out. But it should be in your notes. One of the first geometries we did. Now, I know what the answer is. Something like that? Same answer as the ring, but not with the 2 out front. When we did this, we didn't make this one assumption that Q is very small compared to these charges, but you'll notice I almost always made this charge lowercase q in almost every one of those. And I made these things uppercase Q. That was not an accident. You see, they're very seldom ever going to ask you for the force between 2 charges or more charges. The most likely problem would be that they will ask you to find the electric field at point P in a region of space where there exist 2 charges. You see, we don't really care about what the force is on one charge there. We're more interested in how these 2 charges affect the space around them. That's what we're really interested in. So although we start with Coulomb's law, we start there because you guys can usually handle a discussion about 2 charges because you came in from chemistry and you know that opposites attract and like charges repel. So we spend 2.5 weeks reminding you about the rules of geometry so that we can come to the grips with what I actually want, which is what is the electric field at this location in space? There's a number of ways to find the answers to that question, and we're going to learn one of them right now. And it's the most mundane one. The hardest way to do this problem is to go about what we've been doing all year so long. And that is to find the force that a test charge would experience and then divide out the value of the test charge. That's the procedure. We've been doing this part of the procedure all year. Finding the force on some point charge located at a location in space. What I'm telling you now is that to find the electric field, you still do that process because that's the only way you guys know or know what to do is to deal with Coulomb's law. And then divide by the value of the test charge. So the answer to the question, what is the electric field at point P? Well, I just take all of this and divide by the value of the test charge that was there, which means it's going to be 2qk times z over z squared plus d squared to the 3/2 power. This is the size of the electric field at this point in space. Knowing the electric field means we know what will happen to any charge placed at that location. And because that has more value to us, we tend to look for the electric field more than to look for the force on a specific charge. So again, I'm going to be telling you that for the next couple of days, not even that many, we're not going to learn anything particularly new. What we are going to learn is that you have an extra step for most of the problems we've done so far. I mean, there's not a problem on any of the FRQs that cares about the actual force between two charged particles. All the questions that I have that are FRQs ask you for the electric field. What I've trained you to do is to use Coulomb's law to deal with a multi-body problem to find the force on a test charge. Every one of the problems has been that. The only difference is I didn't talk about electric fields till today. So now every problem has another step, one final step, where when you're done, you divide out by the value of the test charge. So, the electric field. We have a ring of charge. I don't really care, of course, what the force is on a point charge somewhere away from that. I do care about what the electric field is around the ring of charge. So although it's charge ring Q with radius R, we know that at a distance Z away from the center of the ring, there was a force on a test charge that we placed there. I don't want that. I want an expression for the electric field at this point. There's no charge there. But the expression for the electric field at that point, well, that's Q, K, times Z over Z squared plus R squared to the 3/2 power. That's the size of the electric field at that place. Because I know the force there had the 2 Q's. I'm just dividing by the 1 Q that was there. And now this is an expression for the electric field. Now, I know you're wondering, well, what's the point? Well, why bother to do this? Here's the thing about electricity that's much different than mechanics. I've not added much to your problem. I've merely said now that every problem where you had force, we're going to add a step and find the size of the electric field. There's more to it than this, and this is just the start. For example, I can also change this and recognize that in a simple, just solving it for force, knowing an electric field, devoid of knowing anything else, if I know an electric field, I can figure out the force on any charged particle placed at that location in space. The electric field is about the space, the force is about a particle. Good so far? This isn't too bad, is it? Pretty straightforward. There's no math yet, really. Just dividing by little q. We use the construct of the electric field also as a means of understanding the shape of that field in space. Consider, oops, I don't want it either. Consider I have a large charge, a sphere of charge in the middle of an empty space. If I place a test charge right here, everybody in the room should be able to come up with a pretty quick expression for what the electric field must be at this point in space. I mean, you might need some parameters, like, well, I'm going to need something, so maybe it's a distance r away from q, right? I'm putting down a parameter. And I'm saying, all right, so my test charge is q, so the size of that force will be q, k over r squared. So the size of that electric field will just be q, k over r squared. And the direction of that electric field, well, it'll be directed away from Q. So I generally write this as R with a little hat on it. It's in the direction of R. Well, what do you think the electric field looks like at a place right here? Any of this going to be different?
The distance?
The distance has changed, but this still gives you measured by R. What would that do to the force? To make it bigger or smaller?
Bigger.
So I have a bigger force directed away here. If I continue to do this, I could probably begin to build a pattern for what I think the electric field looks like in three-dimensional space around my central point charge. And if I continue this process, are you easily convinced that the electric field around this point charge is going to look something like this? Right, no matter where I consider placing my point, I'm going to be directed with an electric field away from the center. And eventually I will build a pattern that means the electric field probably looks something like this around my central charge. Now, are you clued in a little bit that maybe the concentration of these field lines suggest a larger electric field? And as the field lines kind of get further apart, a smaller electric field? Because that's what this is supposed to be, an electric field diagram. Electric field diagram is supposed to be a device, not a mnemonic so much, but just a kind of a simple way for us to understand what the electric field looks like around an object or a collection of objects. Helps us find symmetries and maybe accept some of the dynamics of what a system might look like. There should be some obvious things. First, clearly electric fields point away from positive charges. That shouldn't be a surprise, but keep in mind, what if I made this negative? How would it change this diagram? Would the diagram change very much? Would the spacing of the arrows change at all? Would the direction of the arrows change? So, if I wanted to draw the version of this where there's a negative charge at the center, do you all realize you would just change all these arrows to point inwards? So electric fields point from positive charges and to negative charges. We say that electric fields originate at positive charges and terminate at negative charges. That's the terminology. Electric fields originate at positive charges and terminate at negative charges. What if I have two identical charges? Except one positive and one negative. What do you think the electric field would look like in a region of space where I have two charges? Sketch it. Just give yourself a quick sketch. It's just... There is a right and wrong answer, but I'm not looking for perfection here. Do a job. What do you think? Just put a test charge somewhere. Anywhere. A couple of places. And begin to think about what the lines might look like for that test charge. The test charge can only tell you one force, but if you start moving that test charge around into space, you might start getting an idea for what these lines should look like. There are some simple rules for drawing electric field lines. First, an electric field line originates at a positive charge and terminates at a negative charge. Also, electric field lines can't cross. They represent what would happen to a particle placed at that spot, and a particle is not going to go in two directions at once. So the field line represents the direction of a single force on that charge, which could be the culmination of multiple objects. So although I know that there's, a force directed that way at this point, and a force directed this way at that point, this charge can only be pushed in one direction at a time. So the field line there should indicate the direction that that particle would be pushed from the combination of the two forces. So, have you tried it out? Have you maybe sketched something? Because I want to come by and see.